Dear learners, welcome to the course Electromagnetic Fields. In this video, we are going to discuss about the derivation of magnetic field intensity due to finite and infinitely long straight conductor. First, we are going to consider infinitely long conductor. Here we are going to discuss how to obtain magnetic field intensity due to infinitely long conductor by using Savart law. In a separate video, I have explained Savart law. This figure 1 illustrates infinitely long conductor which is placed along z-axis. The length of the conductor extends from minus infinity to the plus infinity. We are going to determine differential amount of magnetic field intensity at point P. This is the point P where we are going to obtain magnetic field intensity. The point 1 is a differential current element, ideal vector. So ideal vector is I dz az vector. Since the differential current element is along the z direction, so therefore the differential length along z direction is dz az vector. For our analysis, we consider cylindrical coordinate system. As we know that this dh vector is, according to Savart law, dh vector is equal to ideal vector cross ar vector by 4 pi r square. So from this figure, we are going to write one by one. First we write ideal vector. Ideal vector is I dz az vector. Next, this ar vector is a unit vector along this r direction, along the distance vector. Unit vector along the r direction. So therefore unit vector ar vector is equal to r vector by modulus of r vector. Here we marked point 1 and point 2. Point 1 is the location of differential current element. Point 2 is the location of the point P where we are going to determine magnetic field intensity. So therefore it is represented as r12 vector. It is nothing but r ar vector minus z az vector. So we are going to find the distance vector. Distance vector is nothing but the difference between the ending point to the starting point. Here end point is the point where we are going to determine h vector, and point 1 is the location of the differential current element. So therefore r vector is r ar vector minus z az vector. So we find the magnitude of r vector is root of r square plus z square. So therefore unit vector ar vector is r ar vector minus z az vector by root of r square plus z square. It is equation 3. So according to Savart law, we are going to find the cross product of ideal vector cross ar vector. It is nothing but ir dz a5 by root of r square plus z square. Now we substitute ideal vector cross ar vector by 4 pi r square. So now it is simplified as ir dz a5 vector by 4 pi r square plus z square power 3 by 2. So this is dh vector. differential magnetic field intensity. So from this we are going to obtain the total H vector by means of integrating the entire length of the conductor. Here the entire length of the conductor is from minus infinity to the plus infinity. So therefore dH vector is integrated over minus infinity to plus infinity. So this is the equation 7. So now we consider now we put z is equal to r tan theta, therefore z square is equal to r square tan square theta. From this we find dz is r secant square theta d theta. So now we are changing the integration with respect to theta. So we have to change the integration limit also. So therefore when z is equal to minus infinity, theta is minus pi by 2. Similarly when z is equal to plus infinity, theta is plus pi by 2. Now we are substituting the integration limit and replacing dz by r secant square theta d theta a phi vector. In the denominator it is 4 pi r square plus r square tan square theta power 3 by 2. Here this 1 plus tan squared theta is equal to secant squared theta. So it is simplified as I r square secant square theta d theta a phi by 4 pi r cube secant cube theta. It is integrated with respect to d theta. So now we simplify this expression, we will get I by 4 pi r integration with respect to integration limit is I by 4 pi r from minus integrating limit is minus pi by 2 to plus pi by 2 cos theta d theta a phi vector. So we get I by 2 pi r a phi vector ampere per meter. The equation, this is the magnetic field intensity due to infinitely long straight conductor. So from this we can write what is B vector. B vector is equal to mu H vector. So therefore magnetic flux density is mu I by 2 pi r a phi vector Weber per meter square. So these two are expression for H vector and B vector due to infinitely long straight conductor. Next we are going to consider finite length of straight conductor. The only difference in this case is the integration limit is z1 to z2. In the previous one we consider it is from minus infinity to plus infinity. All other things are same. So here we consider in this figure we observe that the lower end of the conductor is Z1 and the upper end of the conductor is Z2. Upper end of the conductor is Z2. This is the upper end of the conductor Z2. So now we consider the finite length of conductor, which is nothing but Z. Current I is flowing through the conductor and this is the point P. We are going to determine magnetic field intensity. The angle made with respect to the line joining from source to the point 2 is alpha 1, alpha 2. So this is the unit vector AR12 vector. According to Boyce-Savart law, we are going to obtain DH vector is equal to ideal vector cross AR vector by 4 pi r squared is equal to IR dz a phi by 4 pi root of r squared plus z squared the whole squared into root of r squared plus z squared. This is the expression up to this same what we have discussed in the earlier case. The only difference is the integration limit. Here Z1 to Z2. Previously it is minus infinity to the plus infinity. The same way we are writing Z is equal to Z1 tan alpha 1. Z1 is equal to R tan alpha 1. Similarly, Z2 is equal to R tan alpha 2. Now the angle alpha 1 is tan inverse Z1 by R and alpha 2 is tan inverse Z2 by R. So therefore, we change the integration limit from Z1 to Z2 to alpha 1 to alpha 2. So after integrating this, we get H vector is equal to I by 4 pi R sin alpha 2 minus sin alpha 1 A phi vector. Similarly, magnetic flux density is mu I by 4 pi R sin alpha 2 minus sin alpha 1 A phi vector Weber per meter square. So once you understand infinitely long straight conductor, from this we can easily obtain the expression for magnetic field intensity due to finite length of straight conductor. We should give attention to the signs of alpha 1 and alpha 2. So while calculating magnetic field intensity, we should taken care of signs of alpha 1 and alpha 2. So depending upon the position of P, alpha 1, alpha 2 may be positive or negative. You see the figure A. Here the point P is, so you see the figure A. Here point P is below the lower end of conductor. So therefore alpha 1 and alpha 2 both are positive. In figure B, P is above the upper end of the conductor. Here the observation point is above the upper end of the conductor. So therefore alpha 1 and alpha 2 both are negative. Suppose the determination point P is midway between 1 and 2. Here the P is midway between the point 1 and 2. Point 1 and 2. It is midway between 1 and 2. That time alpha 1 is negative and alpha 2 is positive. So we should remember while calculating magnetic field intensity, depending upon the observation point, location of the observation point, the signs of alpha 1 and alpha 2 differ. I hope you would understand the derivation of magnetic field intensity due to infinitely long straight conductor and a finite length of straight conductor. Thank you.